guys, so I just want to quickly go through lesson 4 of accounting for changing levels of atmospheric carbon dioxide. It looks like this on the front page, and it has the box with all the amount of carbon in gigatons. That's page 1, and then page 2, it looks like this with the global carbon cycle. I'm going to make this a little taller so you can see the whole thing. It's not quite working out as well as I had hoped. Sorry about that. Okay, so here's our our carbon cycle, and we have all of our amounts of carbon that's going into and out of different spheres. Mostly what we're looking at is in and out of the biosphere and geosphere, into the atmosphere, and into and out of the oceans, which is your hydrosphere. Okay, so let's look at number 1, which is asking us to figure out the total, I'm going to just read it real quick, figure out the total natural carbon flow in gigatons from the reservoir in the table provided, compare the total carbon uptake from the atmosphere into other reservoirs by natural processes to total emissions into the atmosphere from other reservoirs by natural processes. To do the math, add up carbon stored and subtract carbon released as presented in the worldwide annual carbon flow between the atmosphere and other reservoirs. Okay. And then, actually, let's read the note. The stored carbon, or natural uptake, should be represented as a negative number. So anything that's being stored is negative, since it is carbon that is leaving the atmosphere. So if it's going into the biosphere, or into the geosphere, or into the hydrosphere, it's going to be negative. And then the emissions, things that are going into the atmosphere, are going to be represented by a positive number. So on your table, it has A has the negative sign. Make sure you transfer that over into the answer column, that you put your negative sign over. Okay, so let's look at natural uptake. And when we look at our graph, all of the natural processes are going to be represented with these white arrows. And there's even this circulation, this amount stays in the ocean at any given time. But we have natural emissions from the soil, natural emissions from the plants. Photosynthesis is a natural process that brings carbon into the biosphere. And then we have some of it going into the oceans naturally through diffusion, and then evaporation. Some of it comes out naturally. So let's look for what number 1 is asking for, the natural uptake. So what is being removed from the atmosphere naturally? So this one is the blue numbers going down. So we have 111 and 92. So when you add those two up, you should get 203. So we have negative 203, if I can get my paper to move over. So negative 203 gigatons. And then what do we have being emitted, natural emissions, is we have 50 plus 60 plus 90. So 50 plus 60 is 110, plus 90 is 200. So we have 200 gigatons going into the atmosphere, which if you add negative 203 plus 200, you get negative 3 gigatons. Okay? Being reduced, meaning it's coming out of the atmosphere, it's getting stored. Alright, so let's look at number 2. It says data analysis. Even though rocks, soils, and sediments comprise the largest carbon reservoir, the amount of carbon flow to and from this reservoir is very small. Explain why this is. Okay, so let's look at soil respiration. I need the wrong page. Page 1 has rocks, soils, and sediment on here. And it says carbon emission by soil respiration and decomposition by soil microbes is 60 gigatons. And the carbon dioxide from land use, changes, and burning fossil fuels is 8 gigatons. Note, this is not considered a natural process, but is the result of human activities. So we have to make sure we include both of those things. And then it says the amount of carbon stored from the atmosphere or uptake, and then this varies from location to location, so it's really hard to predict or accurately say the soil always gets this much, because it's going to be different depending on the vegetation in that area, and if it's a complex root system or if it's really shallow roots, you're going to have different levels of carbon dioxide being absorbed by the ocean. Okay, so carbon does, obviously it's in the soil and ground, but when it it's asking us to talk about how it comes out of the ground too. So it's a slow process basically. The amount of carbon to and from is very slow, or very small, because it is such a slow natural process. It takes millions of years for rocks to erode and to have all of that old stuff put back into the atmosphere. So we're going to put down, it is so small because the geochemical, and that's what this process is, process of weathering and erosion, is very slow, very, very slow. Okay, it can take thousands of years, millions of years, much, much slower than what is going on in our oceans with the diffusion and condensation, or evaporation rather. All right, let's look at number 3. I'm going to try this zoomed out. See if that doesn't help. All right, how do overall natural carbon emissions compare to overall natural carbon uptake? So that's these two numbers that we have up here. How do they really compare? Would you expect to see this degree of balance in a natural cycle? In other words, does it make sense when you think about how the natural cycle should function? So hopefully you look and you see, okay, these are really close. Yeah, there's a net uptake of -3 gigatons, but overall, it's relatively a minor difference. And when you factor in animal use, like even just humans basically that throw in some stuff, we can keep it fairly stable. So how do I compare? I would say they are similar, which is kind of what you would expect, because if you have a cycle, you have the products of one thing being needed for the other, and so it has to balance. You can't have it unbalanced, otherwise you would run out of stuff in one of the cycle parts. So either in the atmosphere or in the ground, you would not have, or not the ground, but wherever it's coming from, could be any of the other spheres. If there's not enough, it can't keep the cycle going. So yes, you would expect it to be balanced, otherwise the cycle wouldn't last. Right? You need to have that balance. Next question. I need to fix this so that it's not stuck underneath that stuff. Okay. Now we're going to look at the influence of human activities on the global carbon cycle. We know that we are a big impact on it. So we're going to figure out the total carbon emissions from the combustion of fossil fuels and biomass burning. So combustion is the burning of fossil fuels, and land use changes. And if you look at the article, it talked, or not the article, but the beginning, it talked a little bit about land use. Did it talk about it? I thought it did. Cycle carbon, maybe not. Maybe not. Maybe it's something else I'm thinking of. But anyway, land use would be burning of forest, deforestation, and things like that. If we remove part of the biosphere that actually absorbs carbon dioxide, that's a land use change. Alright, so using the global cycle, Clark carbon cycle, on page 2, we're going to calculate the total emissions from human activities. Now, human activities on this graph are represented with the red arrow. So we're going to look at these two numbers here. And we have fossil fuels, which is our first one, fossil fuel emissions here. And that's a positive sign because it's going into the atmosphere. And that is 6.3. Okay? And then emissions from land use, that is our, I probably should show you this. So we had 6.3 here, and now we're at 1.6 here. Okay, so let's add those two up to get our total. So 6 and 3 is 9, and 7.9, so approximately 8. Okay, so we agree that that's close enough to approximately 8. Okay, so that's a lot of gigatons. Data analysis. Where are most of these carbon emissions going, and what carbon reservoir is taking up this carbon? So all of this carbon in the human emissions Where is it going? Well, our arrows show it going into the atmosphere. So it is going, most carbon emissions are going to the atmosphere. And I'm going to abbreviate it. Whoa. Atmosphere. And what carbon reservoir is taking it up? Well, that's the same answer unless I'm missing something. Oh. From the atmosphere, most places that it is going, so it's getting removed so it's getting taken up by plants. Plants and the ocean take up most of the carbon. Okay, and you know this because if you look at the picture here, once it's in the atmosphere, this is coming out through photosynthesis, so plants, and then going down to the ocean. Okay, so that would be numbers 1 through 5. Let's look at number 6. Let's figure out the total carbon flow. All right. To or from the atmosphere, including flow from human activities. Note, a positive number indicates that the carbon is entering the atmosphere, and a negative number indicates that it is leaving the atmosphere. So, the carbon flow from natural systems, that's going to be our number from, I believe, number 1. And that is, let me just pull that page up. So, natural flow, net natural carbon uptake is right here. That was -3. Okay? So you need to use your number from number 1. What is our carbon flow from human activities? Oh, that's number 4 down here. 7.9 plus 7.9. Okay, so -3 plus 7.9 should give us, and let's make it easy on ourselves, guys. Let's just round this to 8. So what is 8 minus 3? Should get you 5 gigatons. And that's a positive number, which means what? It is going into the atmosphere. 5 gigatons. What is the end result in gigatons of the total carbon flow? So the net ending result is approximately, if we did round, 5 gigatons remain in the atmosphere. Okay? So what's significant? What is the significance of the extra atmospheric carbon dioxide in the Earth's atmosphere? Well, what do you guys think? It's definitely causing some changes. You could pick some of those, or you could be more general. And I probably would be more general with this one and just say, well, carbon is a greenhouse gas, which means it's going to contribute to climate change. So the significance is that all this extra carbon increases Earth's greenhouse gas total. That increases climate change. I'm going to leave it general for climate change and not just global warming, because there's so much more to it than just global warming. Okay? Let's look at number 9. So what's really happening? Scientists are measuring in the annual of 3.2 billion metric tons of carbon dioxide entering our atmosphere from human activities on an annual basis. Scientists say that we're lucky. The ocean is currently taking up more carbon dioxide than it did under pre-industrial conditions. Based on what you know about the emissions of carbon dioxide due to human activities, explain why levels of carbon dioxide, atmospheric carbon dioxide, have steadily increased the entire time carbon dioxide has been measured. So, what do we think? So first of all, this is a little bit old, I would say, because yes, they say we're lucky the ocean is taking it up, but it's costing us because the ocean's becoming more acidic. But why do you think atmospheric carbon dioxide levels have increased steadily since we started measuring it? And hopefully you're thinking back to the Industrial Revolution and realizing that because we're relying on fossil fuels so much, our dependence on fossil fuels has increased, and so our carbon dioxide levels in the atmosphere have increased. So it corresponds. So increased use of fossil fuels since the Industrial Revolution, corresponds to the increase of atmospheric CO2. Okay? So hopefully that makes it all make sense. Okay, and then number 10, bringing it all together. We're going to compare young carbon to ancient carbon. So scientists can measure and track the amount of carbon dioxide human activities emit to the atmosphere. Our activities are like a carbon footprint. The carbon is what our activities leave behind. Compare the carbon footprint of using cow pies, which as biomass for energy, to using fossil fuels. Compare the origin of each energy source. Is it young or ancient? And with regards to the global carbon cycle, why does using young versus ancient carbon energy matter? Okay, so I'm not going to write this one out because this is a long one, and I want you guys to do some of your own thinking on this. But I would like to discuss a little bit about it. So cow pies are the waste products from cows after they've eaten grass, which means that carbon has been absorbed by those plants in a fairly recent time, because plants sometimes, especially grasses, they die out in the winter and they liven back up again in the summer. They go dormant, so they're not really photosynthesizing, and they're not harnessing Earth's energy, or the sun's energy rather. So what you should be talking about in here is how the grass is absorbing or converting sunlight into usable energy through photosynthesis. It's absorbing carbon dioxide, using the energy, making a bunch of energy in the form of ATP, and that's young. It's happening right now from year to year to year. It happens. So that would be your young fuel, right? Versus an ancient fuel, which would be something like your fossil fuels, which the name has it all, says it all. It's fossils, it's ancient, it takes millions of years to make. It's not something that we can renew on a yearly basis. Cows, however, can continue eating new grass on a yearly basis. So it's considered net neutral for what it's doing as far as carbon, because it's pulling something out and that carbon is going right back in. It's the same amount of carbon if you burn the cow pies as what was just being pulled out. So it's maintaining a stable, constant rate of carbon going into and out of the atmosphere, so we don't consider that a harmful process or a harmful source of carbon use. But fossil fuels are really, really old, and they've been buried for millions of years. That carbon has not been in the atmosphere forever. That's only adding to what is in our atmosphere. It's not considered net neutral. So we don't want to take everything that's been stored up for millions of years and put it all back in at once into the atmosphere, because there's no way the carbon cycle can handle that without some dire consequences. I mean, it can handle it, but we'll have some significant consequences, which we're already seeing. Okay, so I think that covers everything you need to know to answer that question in a proper, thorough way. And if you have questions, you can send me an email. I'm happy to answer them tomorrow. Tomorrow's Monday. I probably won't be answering emails the rest of the day today. But if you do have any questions, you can definitely do that. And also you can come see me during pause tomorrow. I will definitely be available. You need to go into your Google Classroom and select the pause link and request access to my pause teams, and then you are free to join whenever, okay? Not just tomorrow, but anytime this week if you would like, especially for help with preparing for the quiz. Don't forget to do your quiz retake. That is due tomorrow at midnight. Okay, I hope that answers everybody's questions. Have a great rest of your day. Bye.